Hi there, welcome to this Elkchemist chemistry video looking at structural isomerism, specifically chain isomerism. So I want to start with the key definition of what a structural isomer actually is. Structural isomers can be defined as molecules that have the same molecular formula but a different structural formula. What that means to us is that these molecules will have the same number of atoms of different elements, but they won't be arranged in the same way along the molecular structure itself. Now in this particular video, I'd like to hone in on a particular class of structural isomer known as a chain isomer. This will apply mainly to organic molecules. So chain isomers are molecules that have the same molecular formula, i.e. the same numbers of atoms of different elements, but a different arrangement of carbon atoms, we're talking about organic molecules, along the carbon chain. So essentially what's going to happen is we're going to create branching off of the main parent or skeleton chain of the organic molecule to create that branching, which will create a different structural arrangement to other variants of that molecule, which also have the same molecular formula, the same numbers of atoms of different elements. So when it comes to structural isomerism and chain isomerism, the best thing I can do is show you actual examples. So I'm going to start with the molecule butane. So butane is a member of the alkane family, and if you remember, the general formula for the alkane family is CnH2n plus 2, and but in organic chemistry as a nomenclature system stands for 4. So I'm looking at a 4-carbon molecule with 4 times 2 plus 2 hydrogens, 10 hydrogens, and it's a linear molecule. So here is my image, my displayed formula, in fact, of a molecule of butane. Displayed formula showing all the bonds present. Now, I could try and construct an isomer of butane that has the same number of carbon and hydrogen atoms, but a different structural arrangement along that carbon chain. Just before I talk about the actual isomer shown on the paper, I want to talk about a common misconception and a mistake that students can make when trying to draw isomers, such as that shown for butane, which stems from drawing a shape which is different without actually changing the structural arrangement of the molecule itself. So here is my model of butane without any hydrogen shown, just the central core carbon backbone of 4 carbons currently bonded together in a straight chain. Now, I could rotate around this central bond 180 degrees to create more of a U shape for this molecule. Now, some students may say that that is an isomer of butane because it has a different shape to my linear 4-carbon chain. But unfortunately, that would be a misconception. This is not an isomer of butane because it's still the same structural arrangement. It's still 4 carbons bonded together in a straight chain configuration. All I've done is twist that chain to create this U-shaped bend. But in reality, it's still the original molecule with a slight twist in it. I haven't done anything fundamentally to change the structure of this molecule. It looks exactly the same. I've simply created a kink. Again, I could change its orientation in space to make it vertical. Okay, it's more of a zigzaggy shape, so it'd look more like this representation of the molecule shown here. But again, this is not actually a different isomer of butane. It's just butane held up at an angle. So you must ensure that the molecule you've drawn is not just a rotation of the original molecule, but has a genuine difference in its structural arrangement. And the best way to illustrate that is that the carbon chain will have a different length to the original molecule. That's the thing to try and draw when you draw an isomer, a chain isomer. So let's now talk about the actual isomer shown on the page itself. And I want to show you how I constructed that isomer. I took a carbon off the end of the butane chain and then took it to the middle of the molecule and created a branch off the central carbon. And that creates a genuinely different structural arrangement, which I'm going to explain to you now. So compared to the original molecule, which had 4 carbons in a linear chain, this new isomer only has 1, 2, 3 carbons in a linear chain. At this point, I had to take my pointer off the page to count the final carbon running down from the center to the branch. So the longest continuous chain of carbons in this molecule is not 4, it's only 1, 2, 3. So it is a genuinely different structural arrangement. Let's look at the displayed formula to make more sense of this. So here is my parent chain, my skeleton chain of 3 carbons in a row, and then the branching carbon coming off of the central carbon is called a methyl group. Why methyl? Well, the YL tells you that it is a branching alkyl chain. It's a branch off the main parent chain of the molecule, which is going to be longer than the branch. And why meth? because meth is the organic nomenclature for one carbon. So in terms of naming this molecule as a whole, we can see that the methyl group is coming from the second carbon of the main propane parent chain. So we're going to try and use that to help us name the structure. 2 tells us where that branch is coming from, and it's always hyphenated into the rest of the name of the molecule. Methyl tells us the length of that branch. This is a 1-carbon branch, so it is a methyl group, emanating from the center of the propane chain, the main body of the molecule itself. So the full name is 2-methyl propane. Finally, to reiterate the key definition of structural isomerism to prove that this 2-methyl propane is an isomer of butane. Structural isomers are molecules that have the same molecular formula, in this case C4H10. Both molecules have the formula C4H10, but different structural arrangements. Butane is a linear 4-carbon chain, 2-methyl propane is a 3-carbon linear chain with a 4th carbon branching from the central carbon. They both have the same number of carbons and hydrogens, but they do not have the same structural arrangement. Just before I talk about the next example, pentane, I just want to say, if you find this video useful, please do give it a like. Maybe think about subscribing to the channel or even ringing the bell to keep notified of our latest videos and content. Your support is always massively appreciated, so thanks very much in advance. So it's worth saying at this point that as molecules get larger, so pentane is a larger molecule than butane, it tends to be the case you're going to have more opportunities or possibilities for different structural isomers, greater numbers of structural isomers to be generated, because longer chains means more opportunity to rearrange carbons along those chains to create those isomers. Again, I'm going to use a simplified molymod model to illustrate the point and visualize these various examples to help you draw them for yourself. So again, imagine I've got a 5-carbon chain, pentane, and I were to pluck the end carbon off of that 5-carbon chain and move it to the center to create a branch, like so. You can see I have a genuinely different structure arrangement shown. I'm going to show you the displayed formula of this particular molecule, talk about it, and then I'll show you one more arrangement after that. So here is the displayed formula of that previous model. You can see that unlike pentane's 5 carbons in a linear chain, 1, 3, or 5, I can only count 4 in a straight chain for this molecule. Then I have to take my pointer off the page to count the final branching carbon here. So it's only a 4-carbon linear chain. So its suffix is butane, and on the second carbon there's a methyl group emanating. So it is 2-methyl butane. Still has the same numbers of carbons and hydrogens as pentane, but it has a different structural arrangement along its central parent chain. At this point, I might as well also just tell you about a simple rule when it comes to the nomenclature of organic molecules. When you do have branching chains off of alkane molecules, you want to ensure that the number given to that branch is as low as possible. So I could have named this 1,2,3-methyl butane, but I didn't, because that would have given it a higher number than my other possible option, which is 1,2-methyl butane. So this is 2-methyl butane and not 3-methyl butane, because our numbering system will always start from the side for an alkane, which gives the lowest possible number to the position of the branching group. Now for the final isomer of the video. If we take a carbon off the end of the pentane chain there and a carbon off the end of the pentane chain there and bring them both to a central carbon in the middle of the chain, we create this rather funky looking cross-shaped molecule, which I'm going to explain to you now. So here is my displayed formula for that cross-shaped molecule. You can see that the longest continuous chain this time is only 3 carbons long. If I draw my pointer 3 carbons along the chain, I now can't count any carbons further in that linear chain. I have to take my pointer off to count the branching carbons coming vertically upwards and downwards from the central carbon itself. So this would be, well, the parent chain is only 3 carbons long, so it's based on a propane parent molecule. And coming off of that propane, we have on the second carbon a methyl group, and on the second carbon a methyl group. So its naming is 2,2-di-methyl propane. Di in chemistry is meaning 2. There are 2 methyl groups present, and we number it twice because it's possible in other molecules that maybe those methyl groups weren't on the same carbon and it might have had a different numbering system. But this is telling the observer with great certainty on the second carbon there's a methyl group, and on the second carbon there's a methyl group. 2, 2, hyphen, di, 2 of them, methyl, what they are, propane, the main chain. So there you have it, guys. How to name and how to draw chain isomers of various alkane molecules. So at the end of the video, all it stands for me to say is I hope that was useful and helps your understanding of isomers and chain isomers in particular. If you want to check out other videos on the channel, they should be appearing shortly in some links above. And finally, just wanted to say thank you very much for watching. I'll see you next time. Goodbye.